All right, guys. So, in this second section of chapter 8, where we're talking about the mathematics of scheduling, we're going to talk a little bit more about the types of graphs that we're going to use in this section. If you remember everything from chapter 5 up through chapter 7, we've been studying graph theory, and this is where we're going to bring some of that graph theory in for chapter 8. As we do so, we're going to have a new type of graph. It's going to have a lot of the same features as our graphs that we've seen before, but this one's a little bit special. It's what's called a directed graph, or sometimes abbreviated a digraph. So a digraph is a graph where the edges have a direction associated with them. Usually we use an arrowhead to indicate that. They're most useful when we want to describe asymmetric relationships. That x is related to y does not necessarily mean that y is related to x. Now, in a digraph, instead of talking about edges, we're going to call them arcs. And every arc is going to be defined with a starting and ending vertex. And we need to respect that order when we write the name of that arc. For example, if we write x, y in that order, that's going to indicate an arc like this, where you're going from x to y. Whereas if you want to describe the arc yx, that would be one going from y to x. So there's always going to be a starting and ending vertex for every edge. So now, unlike in other chapters, it's going to be important which order you write the arcs in. Whether it's xy or yx is going to be an important part of this type of graph. Now, in a digraph, there's going to be a couple of things that we will want to discuss. First of which is what's known as the arc set. And so the arc set of a digraph is basically a set which lists all the arcs. For example, on this very simple digraph where you have x going to y and also y going to x, then you would have both the arcs xy and yx as part of your set for your arc set. When we write the arc set, notice that we use these squiggle brackets in order to indicate that it's a set, and then we simply list out the different arcs separated by a comma. Now, when we talk about an arc like xy, we say that the vertex is either x is incident to vertex y, or we could also say that y is incident from x. When we use that word incident, we're indicating what direction the arc is going. Now, we also have this idea of adjacent arcs, which we've seen in previous chapters as adjacent edges. And we say that the arc yz is said to be adjacent to the arc xy if the starting point of yc is the ending point of xy. Basically, that means that you can go from x to z by way of y. In other words, if we were to draw this out, if yz is adjacent to xy, then what we'd have is x goes to y, and then y then goes to z. Notice that the arrows are important. It's not like we're saying that x goes to y and z also goes to y. So in order for it to be adjacent, you have to have the starting point of one arc at the end point of another. So it has to be one arrow going in and one arrow going out. All right, so then let's talk about what a path is. So in a digraph, we're going to say that a path from some vertex x to a vertex, let's just call it w, is going to consist of a sequence of arcs from x to w, where each arc is adjacent to the one before it, and no arc appears more than once. So it's not as if you're just going to repeat arcs, you're looking to make a trip. Now, the best way to describe that is just to list the vertices in their order of travel. In other words, x to y to z and so on until you get to your end point. In addition to paths, we're also going to have what are called cycles. And for a cycle, you can kind of think of that as a circuit, with a few exceptions. Obviously, with a cycle being for a digraph, there's got to be this direction component. But when we write a cycle, it's actually going to be the case that we can actually write them in more than one way. For a cycle, that's just a path that starts and ends at the same vertex. So I don't know if I had defined a cycle yet. I kind of said it was similar to a circuit, but the actual definition of a cycle is a path that starts and ends at the same vertex. Now, when you write a cycle, it should kind of make sense that you can write it in more than one way. Let's think about this cycle x, y, z, x. So you've got x goes to y, which then goes to z, which then goes back to x. And really, if you think about it, whether you start at x and go x, y, z, x, or whether you start at y and go y, z, x, y, It's really the same cycle. So in fact, in this case, you'd have 3 cycles which were all the same, depending on which of the vertices you wanted to start at. Now, we talked a little bit about degree when we talked about our vertices for a graph in previous chapters. We're now going to have an extra part to that. Our normal thought of a degree of a vertex is going to be replaced by these 2 different types. We're going to have what are called in degrees, and we're going to have what are called out degrees. So the out degree, let's talk about it first, is the number of arcs that have x as their starting point. We'll look at an example of this in just a moment. Whereas the in degree of x is the number of arcs that have x as their ending point. In other words, these are the number that are coming into them. So let's take a look at all this on a graph. So we've got this graph, A, B, C, D, E. You've got all these different arcs. If we were going to list first the vertex set, is just the list of the vertices A, B, C, D, E. That would be this right here. In addition to that, we're going to have an arc set. So we're going to have an arc set with AB, but not BA. Notice that there is not an arrow pointing from B to A, so it's only going to be AB. So be careful how you list these. We also have BD. So we've got AB, we've got BD, we've got AC, which goes from A to C. We also have CA, which runs from C to A. And we do need to list those separately because they are different arcs. They have different starting and different ending points. We also have CD. We also have CE. And then 2 more arcs that we have E goes to A and E also goes to D. So there would be our arc set, would be to list out all the arcs for this particular graph. We could also describe it in this way. A is incident to B, and A is also incident to C, but A is not incident to E because there is not an arc that goes from A to E. Now, A is incident from E, meaning that you can go from E to A. It's also incident from C, meaning you can go from C to A. So if you're wondering how to use that definition or that vocabulary for incident, there's a big difference between saying incident to and incident from. So we just kind of be aware of that vocabulary. Now, let's talk a little bit more about the degrees. Let's maybe start with A. So if you're looking at A, let's first describe our in degree. So our in degree for A is asking how many of these arcs come in to vertex A. That's going to be CA and EA, so you'd have an in degree of 2. We also would have an out degree for A, and then if you look, it's actually going to be the same because A goes to B, A also goes to C, so there are 2 arcs which come out of A, so the out degree is also going to be 2. Let's take a look at D next. So for vertex D, our in degree would be 3. There are 3 different arcs which come in to vertex D. However, our out degree is going to be 0. Notice that none of the arcs which are connected to D actually come out of D, so then your out degree would be 0. Now, something to kind of think about, there'd be a lot of different ways you could get from A to D. You could go from A to C, C to D. You could go A to B, B to D. Lots of different ways that you could potentially get there. However, there is no way for you to get from D to A. They are connected, but the arrows prevent us from going from D to anywhere else. In fact, there is no paths which start at D. All right. Now, because of that, because there are no paths which can start at D, we call it a dead end. There is no possible way for you to start a path at D. There is also no cycle passing through B, because from B you can only get to D, and then from D there is nowhere to go. So it's also kind of interesting how, even though D is a dead end, B almost is a dead end, because once you get to B, you're forced to go to D. There is nowhere else for you to go. So what are some applications of this? Well, one application is traffic flow. If you think about it, there are different streets, one-way streets and two-way streets, that we could use a digraph to represent. Obviously, for a one-way street, we would just have our graph look something like this, where you'd have intersections at the vertices. So maybe this is one intersection A, and here's another intersection B. And if it's a one-way street, we would just draw a single arc going from A to B. If it was a two-way street, meaning you could drive both directions on that road, then you would just have another arc going from B to A. So a lot of times you can use digraphs to represent traffic flow in cities based on whether or not the streets are one-way or two-way. Another application would be telephone traffic. Obviously, when you're wanting to track the telephone calls, someone has to start the call, and then someone else has to answer the call. It's not as if you are necessarily having two at the same time, but you could represent the calls as a digraph. Person A called person B, that would be from A to B. Another example would be tournaments. Anyone that's been in a tournament, whether it be for sports, academics, or whatever it might be, or maybe you've just filled one out in March. In fact, that would be kind of fun to do here in a couple weeks. But tournaments can be represented with digraphs as well. You have to get from the round of 68 teams to the second round, from there to the Sweet 16, and so on and so forth, going from one round to the next. Now, in a tournament, obviously, there is not a kind of two-way arc. It's only going to be going in one direction, which is towards that championship. Now, they can be used basically in any sport, though, that doesn't end in a tie. So some sports like soccer, obviously in the World Cup, that's a little bit different, or even football, you could end in ties. So those would not be necessarily examples of where you would use a digraph for a tournament. The third and final one that I'll talk about is organizational charts. These you could also think of as being like flow charts in a way. Some common examples of that would be the roles in an organization, the corporation for business, the military would use it to assign rank, universities would use it maybe to talk about their delegation of responsibilities. That would be another way that you could use a digraph in a real world context. So you can see that while digraphs are interesting to study just for the heck of it, they also do have some real world uses that might come in handy every once in a while. So let's wrap around back to that example that we talked about at the end of 8.1. Which is where we're going to build that dream home on Mars. Remember, we had that big long task list of all of these different tasks that were incident to or incident from other tasks. They all had different build times. And it's going to actually be a lot more helpful to think about them in terms of a digraph. In fact, here is an example of what that digraph would look like. And now it becomes a lot easier to tell what has to happen before what. Obviously, AP has to happen before IF, which has to happen before PL or IW. And so it's kind of nice to have a digraph to be able to organize all of those tasks into something that's a little bit more visual, a little bit easier to understand. Now, in addition to the normal tasks, we oftentimes will also include an imaginary kind of start and an imaginary end task. Even though these are not really tasks, they are kind of useful in looking at where you would start in the project. In other words, adding in that extra vertex for start indicates that you'd be starting from any of these vertices, AP, AF, AW, and AD. Whereas the end task says that you can end it once you've completed all of these tasks, FW, PD, and EU, which obviously have to be completed after everything else. So now we kind of have the basics of what we're going to need to begin solving that problem from 8.1, this problem of building the dream home on Mars. We now know kind of the basics of how a digraph works, what are the different vocab terms that we're going to be using as we start to look at those algorithms, which will hopefully help us with solving this problem later on in this unit. That being said, until next time, have a good rest of your day.